Hi there, my name's Dr. AJ Kumar, PhD. So, this is continuing the abstract algebra thing, and there's this thing that Artin mentions just in passing that, well, the determinant corresponds to the area of a parallelogram. And he just sort of mentions that in passing and doesn't really explain it. And so I want to explain it in depth. And basically, it boils down to this really complicated looking picture, but really what's going on here is very simple. It's so simple, in fact, that I was able to just figure this out on my first try, and it worked. So, first thing we're going to do is visualize the matrix as column vectors. So, when you take this matrix A and multiply it by x, y, so maybe let me write this out. So if we take A, where is my pink? A, C, B, D times I'm gonna run out of colors. X and let's go with yellow. Y. I do the colors because it's easier for your mind to track the colors. This is equal to x times AC plus y times BD. So you can imagine scaling this vector AC by some factor, some rational factor x, scaling this vector BD by some rational factor y, and then doing the standard tip-to-tail vector addition in order to get their linear combination. And then the AX equals B problem corresponds to, you just put some, new vector out here, and you call this your whatever B vector, and there will be a unique, this is called a linear combination, by the way. You probably know that, but and the matrix being invertible, i.e. these two vectors not being parallel, those are the same thing, that corresponds to there being a unique linear combination of these two vectors, i.e. a unique point xy, so that the sum of that, so that this linear combination equals whatever vector b. This would be the b in our AX equals b. Oh, I have overloaded b, capital B. Right. Anyway, so that's not super important right now. What we're focusing on is the determinant, and I'm hoping that you've seen linear algebra before, so that this isn't totally unfamiliar to you. But this determinant as the signed area, there's a sign to this, namely if you swap the two rows, then that corresponds to swapping the orientation of this parallelogram, and we're going to see more, or not more detailed, but more elaborate way to take this idea in the next video. But in order to understand that, you got to understand this picture. And it looks like there's a lot going on, but really it's very simple. So all I did was took this picture up here, and I did a parallel translate of this green vector up here, and this red vector, or the pink vector over here. And, well, I didn't draw it exactly the same way, and what we're looking for is this turquoise area in the middle. Okay? And so the way we do this is we draw this big red box around the whole thing. And then the remainder you can partition into rectangles and triangles. Okay? Can partition into rectangles and triangles. And so what we do is we take the big area, the red area, which we can measure because it's a rectangle. We know how to compute the area of a rectangle. And then subtract off the areas of each of these little triangles. And what I want you to do is I'm not going to go through why each of these areas, which I've sort of circled here, why each of these are the way they are. I want you to pause the video and convince yourself for each area that this is actually the way that it is, and maybe zoom out and look at this picture as well. Pause the video and convince yourself that each of these areas are what I say they are, and then maybe algebraically try to work out, okay, what is the red area, and then what are each of these little areas, and then take the red area minus each of the little areas, and then see what formula you get. Okay, pause the video, try to do that yourself. All right, so here's me doing it. The area of the red rectangle, well, this coordinate here is a plus b, and this coordinate here is c plus d. So it's a plus b times c plus d. Okay. The area of the parallelogram is a plus b times c plus d minus ac. So we get half of an ac from this green triangle down here, and half of an ac from the orange triangle up here. Okay. Minus BD, so you get 1/2 of BD from this blue triangle and half of BD from this green triangle. Okay, minus 2BC, so you get 1 BC from this orange rectangle and 1 from this lemon green rectangle. Okay, well, you FOIL out that red thing, and that's AC plus AD plus BC plus BD minus AC minus 2BC minus BD, and that is, of course, equal to AD minus BC, which is, of course, the determinant of our matrix A. Okay. Now, what I want you to do, number one, is draw a similar picture and convince yourself that the determinant, so here, I'm going to give you two exercises. All right. Number one, just try to convince yourself using a similar picture that the determinant of A transpose is equal to the determinant of A. All right, and number two, convince yourself, what was the other thing I wanted you to convince yourself of? Oh, convince yourself that if you swap two of the rows, then you get the opposite sign for this. So, clarification. Here we're just doing geometric areas, which are always going to be strictly positive. So you're never going to do this computation and wind up with a negative area for this AD minus, for this turquoise parallelogram. However, algebraically, if you swap the two rows, so the determinant of, what would it be, C, D, A, B? Well, this is equal to CB minus DA, which is equal to minus 1 times the determinant of A, B, C, D. And I want you to try to draw orientations to parallelograms. So try to figure out a way to draw an orientation on the parallelogram, figure out what that means. And figure out which one is positive and which one is negative. Okay, so positive orientation, that means that the signed area is going to be positive, and negative orientation will mean that the signed area is negative, so positive area. All right, let me write it as S greater than 0, and negative, this will be this is going to be s is less than 0. And then what does null orientation mean? So how do you interpret s is equal to 0? Null orientation. Okay. That's what I want you to think about before the next video. All right. Thank you for watching.